SwayamPrabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will start with the vapor absorption refrigeration systems. In this lecture, I will be covering Faraday's experiment, absorption refrigeration, working principle of continuous absorption system, comparison between absorption and vapor compression systems. Now in 1824, Faraday was conducting experiments regarding the liquefaction of the gases. So in one of his experiment, he took silver chloride powder, AgCl powder, in one flask, and he took another flask, created a vacuum and connected these two flasks. And this flask was placed in pool of water. I am repeating, he took a flask filled with the silver chloride powder. This flask was connected to another flask which was placed inside the water, and there was a continuous supply of water. And this arrangement was made for the liquefaction of ammonia. He injected ammonia here, somewhere here through a wall, ammonia vapor. This ammonia vapor was absorbed by silver chloride powder. Then he heated this ammonia, he supplied heat to the flask, heated the ammonia, the silver chloride powder, and the ammonia was liberated and it was condensed here, it was collected here. So liquid ammonia was collected here, and the vapor was condensed and the heat was carried away by the water, cooling water circulated here. But when he started his observations after some time, and this heat was removed because it was no longer required, because all the ammonia was collected here. When he started his observations, he found that this pool of liquid started boiling. It started boiling off, and after a certain period of time, all the ammonia was again reabsorbed by ammonium chloride. This silver chloride. This gave birth to the concept of absorption refrigeration system. It means the solubility of ammonia differs at different temperatures. At lower temperature, the solubility of ammonia in silver chloride was high. But when it was heated, solubility of ammonia reduced and the vapors were generated, which were subsequently condensed in this flask. However, when the heating was removed or the temperature of silver chloride reduced, its tendency to absorb ammonia increased and it started absorbing ammonia available in the flask. Pressure started reducing, pressure inside the circuit reduced, and that pressure became corresponding to the saturation temperature of this liquid, and liquid started boiling off and vapors were generated and they entered to this side, and after certain time period all the liquid available here was shifted to this flask. This gave birth to the concept of absorption refrigeration system. Now what happens in a normal vapor compression system? In a normal vapor compression system, if we look at the pressure and enthalpy diagram, after the evaporator, the vapors enter the compressor. Now at this point, the size of the compressor is decided by the volume of the vapor at point 1. if the capacity of the system is large, definitely volume of the vapor, saturated vapor or superheated vapor available at state 1 will be large. For a very high capacity plant, suppose I want to have a plant of 1000 tons of refrigeration capacity or 3000 tons of refrigeration capacity, you can imagine the size of a compressor. You must have seen the compressor for 1 ton, 2 ton or 5 ton or 10 ton plants. Now, if I want to have plants of this order, the size of the compressor is going to be very large, and there will be some allied problems also. Suppose I am using reciprocating compressor. In that case, reciprocating compressors are not fully balanced. Reciprocating machines are not fully balanced. Some unbalanced force will be there that will create the vibrations. Strong foundations will be required. In addition to that, if I am using rotary compressor, normally to handle large volumes, rotary compressors are used. So, rotary compressors will also require very strong foundation. Size of the compressor will be very large, and the cost of this plant will also be high. Now, if we look at a point 1, the vapor is saturated vapor or superheated vapor when coming out of the evaporator. The volume of the vapor is very large. For example, if we convert this large volume of the vapor into the liquid, the volume of the fluid can be reduced by 1/200 time parts, even more, or it ranges between 150 to 200. So, if I have, suppose if I have 200 liters of vapor here, if I condense this vapor, approximately the condensed fluid will have a volume of approximately 1 liter. This is I am talking about the refrigerants. If you go into the case of water, it is more than 1000 times. So, if I ask you to handle 200 liters of vapor and 1 liter of liquid, definitely you will prefer to handle 1 liter of liquid, because much less energy will be spent in handling this liquid. Now, here we can use the concept of absorption systems. What we can do, we can absorb this vapor in an absorbent, and this is actually being done in a vapor absorption systems. This vapor available after the evaporator, it gets absorbed in an absorbent, and this absorbent, so it is a mixture of 2 liquids, and this mixture of 2 liquids is pumped instead of compressor, because it is a liquid, and in order to handle 1 liter of liquid, the size of the pump will be very small. If I have to handle 200 liters of vapor per second, I am talking about per second, then the size of the compressor will be very large. So, this liquid, we can increase the pressure of this liquid up to this stage P2, and when the pressure is increased, then we can heat the mixture. As we heat the mixture, solubility of the vapor in the mixture will be reduced, and we will get high temperature, high pressure vapor at state 2. So, this is what exactly happens in vapor absorption systems. In absorption refrigeration system, all the processes are same. They have condensers, expansion valves and evaporators. Only this part, compression of vapor, instead of increasing pressure of the vapor in a compressor, the vapor are absorbed in an absorber. Then this mixture is pumped to the high pressure, and here again the heating is done and vapors are liberated. So, in the absorption system, the compressor is replaced by an absorber, generator and pump. So, where the vapors are generated, it is known as generator. I will define them one by one. The absorber. In absorber, the absorption of refrigerant vapor by its weak or poor solution in a suitable absorbent or absorbent, forming a strong or rich solution of the refrigerant in the adsorbent. So, here in the absorber, the vapor is absorbed in an absorber. It is known as absorber. Now, second part is generator. Now, in generator, the heating is done, heat is given and vapor is liberated. And third is pump. Pump, the function of pump is to increase pressure of low pressure liquid to high pressure liquid. So, vapor absorption units are mainly heat operated units. and the movement of refrigerant into the absorber is done by the pressure depression in the absorber. Now, I will take a typical example of continuous refrigeration system, because the Faraday system was intermittent system. In intermittent refrigeration system, one flask you are giving heat and another class you are collecting liquid, and then heat is removed and this fluid boils off and you get refrigeration effect. Now, in order to repeat cycle, again the heat has to be given, then liquid will be formed, and then again liquid will be evaporated. So, this is an intermittent cycle, and for actual practice we need continuous cycle. So, in order to have a continuous cycle, there has to be one absorber, where vapor will be absorbed, where vapor will be absorbed coming from evaporator. This is evaporator. And absorber has temperature, evaporator has temperature TE, and it is taking heat QE. Now, vapor from emerging from the evaporator, they are entering the absorber. Now, here absorption takes place. During this process of absorption, heat is liberated and heat is sent to the surrounding at TA. So, this is QA. After the absorber, a pump is used to pump the fluid to the generator. This is generator where heating takes place, and heating can be done from some external sources. Normally in absorption systems they are very useful where waste heat is available. So, waste heat can be used for heating in the generator. It has temperature Tg and the heat transfer is Qg. Now, after generator, it goes to the, as in the case of vapor compression system, it goes to the the condenser, and in condensation also the heat is rejected, Q condenser, and outside temperature is TA, ambient temperature. And this is, and we assume, here there is an assumption that temperature difference between this and condenser and outside is negligible. Now, after the condenser, it goes to the expansion wall as usual and then to evaporator. Now, for continuous operation of this unit, this is absorber, this is generator. In absorber, there is a rich solution of refrigerant into the absorber. It is pumped, and here, because the vapor is liberated, this becomes lean solution. So, lean solution is again sent back to the absorber, and that is how the cycle is completed. Now, in this cycle, in continuous operation of absorption system, if I want to do the analysis, because for analysis purpose we need the coefficient of performance. So, if here I want to have coefficient of performance, first of all I will do the heat balance. So, heat balance is QC condenser and absorber plus QA is equal to, because it is heat rejected, and heat supplied is QE plus QG plus work of the pump. This is energy given to the system. All the processes are ideal processes. So, change in entropy of the system is 0. So, QC plus QA divided by TA is equal to QE divided by TE plus QG plus WP divided by Tg. So, we have taken that entropy, sum of change in entropy is 0, and this is heat balance. Now, if we divide this equation by TL, then we will be getting QC plus QA divided by TA is going to be equal to QE by TA plus QG plus WP by TA. Now we have two equations. These two equations, this term is common, so we can always write QE by TE plus QG plus WP, this is work of the pump, divided by TG is equal to QE by TA plus QG plus WP by TA. Now, if we further rearrange these terms, we will be getting QE 1 by TE minus 1 by TG. So, QE by TE minus here this is A, TA, because this term is taken to this side, so QE will be common. So, QE by 1 by TE minus 1 by TA is equal to QG plus WP 1 by TA minus 1 by TG. Now, I am repeating, I have taken heat balance, right? Heat coming to the system is QE plus QG. QE means heat is taken into evaporator, heat coming to the generator, work by pump is equal to heat rejected. It is condenser, heat rejected in the condenser, heat rejected in the absorber, because during absorption process there is a heat rejection. We have considered the change in entropy in the respective process, we have taken the change in entropy. Now, this equation of heat conservation is again divided by TA, it is divided by TA. Now, we have these two equations. Now, in these two equations you can see this is equal to this, they are same. So, this is equal to this. So, this equivalence we have taken here, we have rearranged the term, this is in bracket. So, we have rearranged the terms. Now, COP of the system is refrigerating effect, that is QE, heat transfer taking place in the evaporator, plus energy input in the system. In vapor compression system it was through compressor, now here it is QG plus WP, work of the pump. In some of the books you will find that work of the pump is neglected, because if you compare this heat transfer and this energy and this energy, this can be neglected, but here in the expression we have considered it. So, this ratio is going to be from this expression, it is going to be equal to 1 by TA minus 1 by TG divided by 1 by TE minus 1 by TA. And COP again, COP is going to be equal to TG minus TA divided by TA TG, TA minus TE divided by TA TE. So, this can be cancelled, and COP of the system we can write as TE divided by TA minus TE multiplied by TG minus TA upon TG. Now, this is the expression for the coefficient of performance of any this vapor compression refrigeration system. Now, here if you look these expression individually, TG minus TA over TG, TG minus TA over TG means a Carnot cycle working between this temperature and this temperature. The efficiency of the Carnot cycle can be expressed by this expression, and multiplication of these two will give the COP. Now, this temperature is difference between TG and TA. TG minus TA is known as lift, temperature between generator and absorber. Temperature difference between absorber and evaporator is known as depression. Now, for a better performance of the system, the ratio of L by D should be less than 1. I will take one example here. In this example, there is a vapor absorption system working with Tg is equal to 90 degree. 90 degree centigrade is Tg, and Ta is equal to, so 90 degree means Tg is, so absolute temperature is 363 Kelvin. Now Ta is 40 degree centigrade, so absolute temperature of Ta is 313 Kelvin, and evaporator temperature is minus 15. So minus 273 minus 15 is 258 Kelvin. Now we have temperature here 90 degree centigrade, this temperature is 40 degree centigrade, and this temperature is minus 15 degree centigrade. COP of the system. Now in order to find COP of the system, it is going to be TE divided by TA minus TE multiplied by TG minus TA divided by TG. So if we take TE is 258 divided by TA 313 minus 258 multiplied by 363 minus A, TG minus TA 313 divided by 363. If we solve this, COP of the system is 0.646. Now the second is, if evaporator temperature falls to minus 20, suppose this temperature instead of minus 50, it is reduced to minus 20 degree centigrade. What should be the generation temperature in order to maintain the same COP? Now if this temperature is reduced, such type of issues creates a lot of problem in vapor compression system. But here, first of all I will solve it, then I will explain. So here, now COP, this TE, it falls to minus 20 degree centigrade, so it becomes 253 Kelvin. So when TA becomes 253 Kelvin, now T is same, 313 is same, 253 Kelvin. Now TG we have to find now, TG we have to find, TG, and this is TG. And COP is remains same, 0.646. Now if we solve this and try to find the value of TG, the value of TG is 369.63 Kelvin or 96.6 degree centigrade. So in this absorption system, if we reduce the temperature of evaporator, simply in order to maintain same COP, simply we will have to increase the temperature of generator. So it can be easily compensated, because easily the COP can be maintained. This type of arrangement is not possible in case of vapor compression systems. Now third is, shall the energy requirement in the generator will change? The energy requirement in generator will change or not? The energy requirement in generator will not change. Only temperature, because the temperature of energy addition will only change. So in the generator, same amount of energy will be required for same refrigerating effect, because if the temperature is going down, we are assuming that refrigerating effect is same. So if refrigerating effect is same, in that case in order to maintain same COP, the energy addition in generator will be at 96.6 degree centigrade. Now we will make a comparison between absorption and vapor compression system. So if you compare the absorption system and the vapor refrigeration system, the quality of energy in vapor compression system, a compressor has to run, and compressor shall run with high grade energy, work will be required, and here in this case only heat is required, and that too if waste heat is available that is if waste heat is available, then we get a refrigerating effect almost free of cost. It has less moving part, so friction loss is less. Quality of refrigerant vapor. Now in vapor compression system, we have to ensure that the quality of vapor which is leaving the evaporator, it has to be superheated or at least saturated, but same is not the case here. evaporator pressure, in this case, in vapor compression system, if the evaporator pressure goes down, the performance of the cycle is drastically affected. I mean, in a pH diagram, if I reduce the pressure in the condenser, the performance of system will be drastically affected, right? It will be because refrigeration effect will reduce and the energy consumption will increase. But here we have seen in the previous numerical, by slight manipulation of temperature in the generation, the COP can be maintained. Capacity, we can go for very high capacity in case of absorption refrigeration plant. In fact, the plants of 3000, order of 3000 or 4000 tons of refrigeration capacity are recommended to be the absorption refrigeration plant. Maintenance is low. Wastage of refrigerant is not there because in vapor compression system they operate on very high pressure and leakage of refrigerant is always an issue. So here the wastage of refrigerant is not there as you compare with the wastage of refrigerant in vapor compression system, and it occupies less space. It does not require any robust foundation for compressor, and there are many more issues which make vapor absorption system superior to vapor compression system, especially in the case of high tonnage of cooling. These type of systems are not economically viable for low capacity systems like 1 ton, 2 ton refrigeration. For those capacities, vapor compression refrigeration systems are recommended. Now, this is all for today's lecture. Tomorrow we will discuss some of the specific vapor absorption systems.